If you're interested in getting started in electronically assisted astronomy, you're going to need some sort of camera. So in this video, I'm going to walk you through the different camera features so that you'll be better able to determine which camera is the right camera for you. Now this video is part 2 in a series of the 6 essential items that you need to get started in electronically assisted astronomy. If you haven't seen part 1, you can take a look at it here, where I discuss the essential features in choosing optical tube assemblies and mounts for electronically assisted astronomy. I'll put links to some of the cameras that I discussed today that I think are highly applicable to EAA, as well as some of my favorite astronomy equipment vendors down below the video. And I would appreciate it if you would use these links when you make your purchases, as it will help support my channel and future videos. We're going to need a camera to replace the eyepiece, because that, after all, is the basis of EAA. And it wasn't that long ago that the only choice that we had were analog video cameras. Now in the late 90s, people realized that security video cameras were actually very good for low light conditions and could be adapted to telescopes to give very amazing views of deep sky objects, and those were the early days of EAA. Now it didn't take long for several different vendors to take and modify those security video cameras to make them better for electronically assisted astronomy by increasing the maximum length of exposures, adding cooling, adding external control functions, and so forth. However, if you don't already have one of these video cameras, I suggest you don't invest in an analog video camera going forward. The hobby made a big transition starting in around 2015, when a company called ZWO, based in China, introduced the world's first low read noise, high sensitivity CMOS cameras for astronomy. Now this caught on in the EAA world, and it didn't take long for other vendors to supply similar cameras. Now these analog video cameras are still available today from companies like Revolution Imager 2 from Orange County Telescopes. But unless you already have one of these, I suggest you don't invest in analog technology. It's an old technology. Now it used to be that the CCD sensors in these analog cameras were much more sensitive than the competing technology known as CMOS, which is available in cameras like this one here. But around 2015, CMOS sensors became available, which had very good sensitivity, on par with CCD sensitivity. In fact, so good that the two main suppliers of CCDs decided they were no longer going to build CCDs and concentrate on CMOS only. Now there's several reasons why we like these CMOS cameras better than these analog cameras with the CCD sensors. First of all, as I said, the CMOS sensitivity is greatly improved. Second, the CMOS sensors that we get here compared to the CCD sensors in these cameras have much smaller pixels, so we have much higher resolution than you can get here. 2, 3, and even 4 times the resolution. 3, the CMOS sensors that we have in the cameras today are much bigger than the ones that are available in these analog cameras. So much bigger, in fact, that you can get them the size of a 35mm DSLR camera. This analog camera here, the Revolution Imager 2, has a 6mm diagonal sensor. That's like using a 6mm focal length eyepiece. So that means you have very high magnification with this. It can be very hard to find and center targets at such a high magnification. Even this one only has an 8mm diagonal chip. Now, CMOS also has cameras with 6, 8, but it goes up 12, 16, 23, even up to 35mm diagonal. So you can get very large fields of view, and you can size the field of view of the camera to your pocketbook and your optical system. Fourth, the other advantage of these CMOS cameras that came out around 2015 is these are very low read noise. In fact, the read noise is so low that we no longer have to take long exposures, 30 seconds, 1 minute, to really see things. Instead, we can take extremely short exposures, 10 seconds, 5 seconds, even 2 seconds long, and stack multiple frames of those very short exposures to see the same thing we would see with a single very long exposure. Now, what's the advantage of the short exposure? It has several advantages. Number one, we don't need an equatorial mount. We could actually do work with an alt-az mount because the exposures are not long enough to show field rotation. Two, and even if we're using an equatorial mount, we don't need the highest grade equatorial mount like we do in astrophotography because we're doing very, very short exposures, and the live stacking software will take care of any small drift in the field of view as we stack subsequent images. And the last reason these CMOS cameras are better than the analog cameras is because these are security cameras. The menus on these things are very confusing to people. The menus have nothing to do with astronomy. It has to do with setting up a security camera. Whereas these are astronomy cameras, and the menus are very, very simple and meld very well with the live stacking software we'll talk about. So it makes it very easy to get started and understand what you're doing. Now, there are many different companies out there making these CMOS digital cameras. The cameras I have here are from a company called ZWO in China. There's also QHY, SV Boni, Player One, TubeTech, and TubeTech sells their own products, but they also custom make for companies like Agena Astro, Rising Sun, who rebrand and sell the TubeTech cameras under their own name. So who makes the best cameras? Well, consider the following. The majority of the camera's capabilities are determined by the sensor inside the camera. And the sensors are not made by the people that you buy these cameras from. They're made by one company, Sony. And Sony labels them IMX with a 3 or 4 digit number. This has a Sony IMX224 chip in it. This has a Sony 2600 chip in it. There's 533, 178, 183, so on and so on. And many of the manufacturers, like ZWO, name their camera after the chip inside it. So ASI 224 tells you right away this has a 224 chip in it. And QHY does the same. And some others do exactly the same. So you can tell right away which chip is in there. Even if they don't use the chip number in their name, you can look it up in the specs. And so the point is, the chip is determining the majority of the features of the camera. The chip determines the spectral sensitivity, the resolution, the chip size, so the field of view. It determines the read noise. It determines the deep well. It determines the ADC, etc., etc. So when you look from one company to the next, the differences between them tend to be more subtle than major. So how do you distinguish from one vendor to the other? Well, first of all, price is one of the main differentiators. Second, some will provide USB hubs, whereas others don't. If it's a cooled camera, they can each use different kind of cooling mechanisms. Some will even have dew control with dew heaters on the window so that the sensor doesn't freeze up. A major difference will be in the packaging, the design, and shape and size of the camera itself, and a few other subtle things there. So what I'm saying is there's not really a whole lot to differentiate from one vendor to the next. So the differences can be very subtle and can come down to which company you think is the better company to deal with, and also price. So how exactly do you decide which camera is right for you? Obviously, cost is one of the biggest drivers, and you can find cameras for under $200 to many thousands of dollars. But I would say the sweet spot for a non-cooled camera being used for EAA is somewhere between $400 and $600. But if you wanted a cooled camera, it would be under $1,000. So there's a couple of things you need to decide first. Number one, do you want cooled or uncooled? This is an uncooled camera with a small chip in it. This happens to have a very large chip in it, but it's a cooled camera. And you can see that the camera body is going to be much bigger for a cooled camera. In fact, most of the space in here is air for the fan to help cool the Peltier cooler that's inside here that keeps the camera cooled. Now, unless you're planning to do astrophotography, you really don't need a cooled camera for EAA, Cooling adds about $200 to the price of the camera. Also, with an uncooled camera, you're going to use almost no power at all. These uncooled cameras use less than 6 watts. Some are only 2 or 3 watts. The big chip in this actually only uses 6 watts. But with the cooling, you need an external power supply, which can be anywhere from 15 to 35 watts of extra power, depending on where you set the cooling on the camera. The other thing to note about the cooled cameras is because the body is so much bigger, you have to worry about clearance on certain kinds of mounts. And this camera will absolutely not clear the base on one of these SE or the Evolution mounts from Celestron or similar mounts. So keep that in mind. Now, the advantage of cooling, any CCD or CMOS chip is going to have a certain amount of thermal noise. And so that means that you get random signal on the pixels due to temperature. The warmer it is, the more thermal noise. The onboard thermal cooling on a cooled camera helps to mitigate that thermal noise. Now, on the other hand, even though a camera like this that's not cooled doesn't have a mechanism to keep the thermal noise low, you can do things called dark frame subtraction. So you can subtract out some of that noise right in the software that stacks the images live and still beat back quite a bit of the noise. So my recommendation is, if you're not planning on doing astrophotography, and if your budget is tight, you can very well get away with an uncooled camera. My first camera was uncooled, my second camera was uncooled, and because I'm starting to do more astrophotography as well, I finally got a cooled camera. So, cooled or uncooled, the choice is up to you. The next thing you need to decide is whether or not you want a color or a mono camera. Now, obviously with a color camera, you're going to be able to see all of the colors that are associated with the different nebula. The stars out there of different colors will show up, and you'll see the red star-forming regions and galaxies and so forth. Now, I personally like to see color, so I use color cameras. Now, the alternative is a mono camera. Now, in order to understand the difference, I think you have to first understand, how do they make a color camera? Well, all of the chips that they make are intrinsically mono, meaning the pixel itself is sensitive to any color of light that impinges on it. Now, the way that they make a pixel sensitive to different colors is by putting a color filter over top of that pixel. And so they arrange color filters, 2 green, 1 red, 1 blue, in a square matrix called the Bayer color matrix, after the Kodak gentleman who invented it. So any light of a different color that impinges on a green filtered pixel will not get through. And so that's how you get a color out of the camera. Now, the downside to that is you're throwing away all these photons of different colors in these pixels that are filtered red, blue, and green. And on a mono camera, there are no filters. So the exposure times in mono cameras are much shorter to see the same amount of detail. However, what you're seeing is simply in black and white. So that's one of the choices you have to make. Also note that the mono cameras cost about $200 more than their color counterparts. And why is that? I suspect it's because there's a lot less mono chips being made and marketed than there are color chips. Now, the next thing to consider in choosing your camera is the chip size. Now, the chip size, along with the focal length of your telescope, will determine your actual field of view. So the chip width or height divided by the focal length of the telescope times a multiplier will give you the field of view in arc seconds. Now, this camera, which came out in 2015, the 224, has a 6mm diagonal chip. This is about the smallest chip that anybody uses. And if you look on the forums these days and you ask, hey, should I buy this camera? Most people are going to tell you, no, don't buy this camera because you're going to have a lot of trouble with this. And what they mean is, with this very small field of view, you're going to have a very good go-to alignment in order to find the target. Keep in mind, we're looking at deep sky objects, which at best, in a very large telescope with an eyepiece, look like a little smudge. So you're really not going to be able to identify it unless you're on target. Now the diagonal of the camera is like the focal length of an eyepiece. So this 6mm diagonal camera is like a 6mm eyepiece. You wouldn't start off, if you're doing visual, using a 6mm focal length eyepiece to begin with. You typically will start with 28, 30, 32mm focal length eyepiece, something with a much larger field of view. So the recommendation is you're much better off investing in a chip which is much bigger, that will give you a larger field of view and make it a lot easier for you to find targets. So even though you can find these 6mm 224 cameras for under $200, I would avoid it if you can. Now, on the other hand, when this first came out, everybody jumped on these. We are all excited to have these. We figured out how to make it work. Yeah, there was some frustration if we didn't do a good go-to alignment, but we learned how to find the targets with these things. But if you want to make your EAA experience a lot simpler and a lot less frustrating, go with a bigger chip. Now there are chip sizes around 6, 8, 9. I recommend 12mm and higher as a starting point. And we'll go through some of the cameras and camera specifications a little later, and you'll see some of the cameras that I think are pretty ideal, and other folks post on the online forums all the time and say they're very happy with. Now the caveat to that is the bigger the chip size, the more expensive the camera. And shortly I'll show you a table with a bunch of different cameras, and we can run through the chip size and the camera cost and the other attributes so you can see what some of your options are. Now you do have to be careful as the chip size gets bigger, because the camera, it becomes more and more susceptible to vignetting. And vignetting is simply the fact that as the light comes down through the optical path, any restrictions in the diameter of the optical path as you get closer to the sensor will prevent some of the light on the outer edges of the field of view from reaching the camera. So you will see an intensity variation from center to edge of your field of view. And that could get pretty darn obvious if you have a lot of restrictions in the light path and couple that with a very large field of view sensor. Now there are several ways around that, and one of them is to mechanically make sure that you have no obstructions in the light path. Make sure that any extensions that you have to add to between your optical tube and your camera are wide enough so as not to add any additional vignetting. And the other thing is you can take care of that with something called flat frames, which takes into account the intensity variation across the field of view as it stacks each image into your final total image. So there's one more item that we should talk about when trying to size the camera to our optical system, and that's image scale. Now, image scale, simply put, is a measure of how much of the sky shines on each individual pixel. The larger the image scale, the bigger the area of the sky that falls on the pixel. Now obviously, if we want good resolution, we want each pixel to look at a small portion of the sky. Now the image scale will depend on the size of the pixel divided by the focal length of your optical system. So the smaller the pixel, the smaller the image scale, ostensibly the higher the resolution. The longer the focal length, the smaller the image scale, and ostensibly the higher resolution. Resolution is not completely determined by your image scale. In all likelihood, your resolution may very well be determined by the local seeing conditions, which means that you have turbulence in the air that changes the refractive nature of the column of air you're looking through. So it spreads out the image over some area determined by the amount of turbulence in the air. And typically, the local turbulence leads to a seeing condition on average of about 2 arc seconds. Now, sampling theory tells us that we want to have an image scale in our optical system of between 1/2 and 1/3 of the seeing that we expect. So we'd want to be somewhere around 0.7 to 1 arc second per pixel. So determine what your telescope focal length is going to be and use this equation, which tells you the image scale based on the pixel size of the camera you're looking at and the focal length that you're operating at. Now there's one other practical consideration to this. We typically will use a telescope with and without a focal reducer, which means we're actually going to have two focal lengths on a telescope like this. And with an SCT using Hyperstar and a focal reducer, we have the native f10, we have an f7 or f6.3 if we're using a non-edge telescope, and then we have f2. So that we have three different focal lengths that vary from over a factor of 5. Now, one camera is not going to give you the ideal image scale for all of those cases, but most of us are not going to be able to go out and buy a different camera for each focal length that we're dealing with. So don't get wrapped around the axle on this image scale thing. Match the pixel size of the camera to the longest focal length that you will operate at, so that you have sub 1 arc second per pixel. That way, when you're using the shorter focal length version of your optical setup, you can bin the camera by combining adjacent pixels to effectively make the camera have twice as big pixels as far as it's concerned, and you can offset some of that decreased focal length and try and keep the image scale still down below 2 arc seconds per pixel. So I know that's a lot to digest if you're new to CMOS cameras and EAA. So I put together this table to help explain some of the differences among the cameras and give you some idea of what you might be interested in for EAA. Now I'm using ZWO's cameras like the ASI 224MC and so forth as an example, but remember that sensors are made by Sony. So this IMX 224 is found in their ASI 224MC camera, but it's also found in cameras from a lot of other vendors, and I've seen it as low as 179 from another vendor. The parameters listed below, diagonal resolution, read noise, 0 amp glow, etc., these are wholly dependent on the sensor. So that's out of the hands of who sells you the camera. What's in their control is the price, whether they have cooling. These are all uncooled cameras here. These are cooled cameras down here. The size, shape of the camera, how they do the cooling, and a few other things. Those are determined by the folks that take the Sony sensor and build it into a camera. So you'll look for those differences among the camera vendors in addition to price differences. Now, as I said, these are all uncooled cameras, and what I highly recommend if you're first starting out to do EAA and you're not planning to do astrophotography. These are all cooled cameras, so if you're planning to do astrophotography, you might want to consider one of these. Now, I did put this camera in here, the ASI 2600, which is the big camera you saw earlier in the video. I'm not recommending that for EAA. Of course, you could always use it for EAA, but I bought this camera for astrophotography, so you don't really have to spend $1,800 for EAA. But this camera has a very large chip. It's a 16-bit ADC and so forth, so that's why it is expensive. But you don't have to spend more than $1,000 if you want a camera for EAA and astrophotography. And if you just want it for EAA, you actually don't have to spend more than, say, about $600 if you look at this table. Now, the other thing to point out is the diagonal. I spent a lot of time talking about that. I don't recommend the ASI 224 because of its small diagonal size. It makes it very hard to find things unless you're really careful about your go-to alignment. But the fact of the matter is, when that camera first came out, that's all we had, and we were excited to use it. Tons of people bought them, and we made them work. So just be aware that it's probably not your first choice unless you're really strapped for cash, in which case this would be the cheapest camera you could get. And as I said before, I recommend cameras that are somewhere in this range of diagonal, which will make your life a bit easier. But this 178, people have used this for a long time. There's a new version, new camera out here, this 678, which has some advantages over the 178. But again, these are both fairly small chips, but not impossible to work with if you're patient and careful and you don't mind getting frustrated, and you'll work through it. But in general, I like to recommend these 12, 13 micron chips or larger. And you can see these aren't really that expensive for most people. Now I realize for some people this is a lot of money. That's why I give you options. One of the most popular ones these days is the 533, and that's because it has a pretty good resolution, it has a fairly large diagonal, and it has this 0 amp glow feature. Now amp glow is the name given to the effect of light, infrared light, coming off the supporting circuitry next to the chip itself. So there's a lot of electronics around that drives the chip, and when that runs for a while, especially if you're doing long exposures, it heats up, and when things get warm, they give off infrared radiation. And no surprise, our sensors are very sensitive in the infrared. So you'll see sort of a bright region in a corner or side of a chip, and that's called amp glow. So these cameras that say yes to 0 amp glow have a feature that gets rid of that amp glow. This one here has circuitry that helps to minimize it. These other ones don't have that, don't have either of those. So they will have amp glow, but look at this ASI 294. This doesn't have any anti-amp glow feature as well, but people deal with that by using something called dark frame subtraction, which we'll mention in the next segment on live stacking software. So you can pick a camera with the 0 amp glow. That seems to be these newer cameras of the 585 and the 533 have that. But if you prefer this camera for some reason, and lots of people have been using this 183 for a long time, don't worry about the fact that it does have some amp glow. You can deal with that. Now, what else to be said about this? So you'll see that a couple of these cameras, the 183 and the 533, also have cooled versions. You'll see those down here. So they have the same specs otherwise. It's just the price and the cooling for obvious. It's just that with the cooling, the price has gone up, as you would imagine. Now, another very popular camera that is used for astrophotography and also EAA together is this ASI 294. This camera's been around for quite a while. It has a pretty large diagonal chip. So if you're doing astrophotography, you might consider this as well, and it will work fine for EAA. So there are some ideas here for cameras. Of course, there are even more expensive cameras than this. There's lots of variations of cameras out there. These are not all the sensors that Sony makes. So you can find loads and loads of other cameras to choose from. But I think for EAA, these are the ones that you would consider. And frankly, I think, you know, the ones in this region here are probably the most popular ones out there. Like I said, these two are relatively new, and people seem to like them a lot, kind of supplanting this 183 and the 178, which people used in years past and still have them. But now these are the cameras that people seem to be buying, either in the uncooled or the cooled version. So that does it for the third essential item for EAA, which is the low read noise CMOS camera. Don't forget to like this video and subscribe to this channel so that you can be informed when I release part 3 to this video series on the 6 essentials for EAA. In that next video, we'll discuss live stacking software. And if you want to see more content on astronomy equipment and techniques, please visit my website, californiaskies.com.